Okay, so I'd like to welcome you back to the Chern-Weil Symposium. The next speaker is Vesselin Dimitrov. He graduated in 2017 from Yale. He has known for his proof of the number of results, including the Schinzel-Zassenhaus conjecture about polynomials and other results. I always find that this is a good secret for mathematics, is the way to succeed is having brilliant collaborators. I learned that from Benson. That's what he always tells me. And that's what I've done in my case. So he's also a collaborator of mine. And so I'd like to welcome him. Give the next talk.
Thank you very much. Thanks for having me. It's an honor to be here. My talk will be about results, old and new, about using methods from transcendental number theory. That refers to the algebraization part in the title. The square root method, as I hope to explain, will actually make a reference to this Schinzel-Zassenhaus theorem that was mentioned. A new part is to eventually be able to say something about the Dirichlet series in the context of arithmetic algebraization methods. So the paradigm of lower bounds on algebraic quantities that are not equal to zero is the Liouville effective explicit Diophantine separation inequality, and just recall one form of it. In some sense, the methods that based on the arithmetic of power series instead of Galois theory and norms and discriminants, resultants, and constructions from in algebraic number theory. So the method will be trying to get around using the Liouville bound and get alternative and sometimes actually better results, but also some approaches to the world of true L functions in which are in number theory, like Dirichlet series, which are not and particularly the zero spacings and separation for Dirichlet series are well outside of this algebraic number theory world. So the veil height, absolute veil height, is this canonical height function on the algebraic points of the multiplicative group, with torsion, which is zero precisely on the roots of unity. And I think the notation that follows that this normalization of the absolute values, which is actually spelled out here, so uniquely characterize this object. So there has to be, this notation actually depends on the choice of the number field, but the height of alpha as defined here is independent of a choice of a number field K containing alpha. So strictly the absolute value of the rational place P is normalized by raising it to that power, to this power. So it's divided through by the global degree of the number field. So this formula will hold when we restrict to the field Q. So this is just a convention of notation, if big H will denote the exponentiated height. And so the product formula in number fields is the general version of this Liouville bound. So it says that for by definition, this definition of the height is exactly the minimal quantity, such that for all subsets of the places, there's this two-sided bound, and in particular when we have, of course, for non-zero elements. And so it gives a separation, a lower bound for algebraic numbers that are not equal. So applying this inequality to alpha minus beta with the triangle bound, it gives this. And I just wanted to spell out this particular case where we have a place, Archimedean place, given by complex embedding of the algebraic numbers in C. This is how these normalized absolute values unwind, and so we get a separation bound which is at least, there's this two-factor, at least exponential in minus the degree of the number field generated by alpha and beta. Otherwise, this big H is the absolute multiplicative height. And let's see where we get on when we apply this general principle to Salem numbers in a fixed interval. So, for example, in interval 1 to 2, remind you of the definition of a Salem number. These are reciprocal algebraic integers. So there is an integer monic polynomial equation P of x, which has roots at lambda and 1 over lambda. But all the other complex roots belong to the unit circle. If I set to the closed unit disk, that is the same, would be the same definition. And so the Weil bound, because in general this degree of when we adjoin both alpha and beta is provably close to its upper bound by theorems of Amorose and David in the Diophantine analysis. This general, in any case, we have this upper bound on this degree, and the separation bound is quite bad. It's exponential in minus n squared. It seems to be all that it gives. But in the other direction, so from the proof of, this is the construction of Salem, which this notation means the derived set of the Salem numbers is at least, yes, apologies, it contains the Pizon numbers. So that means that starting with your favorite Pizon polynomial, like here, you can construct a two-sided sequence of Salem numbers converging from both sides. Pizon numbers are bounded away from one, and the convergence rate is equal to the Pizon number itself. It's exponential in minus n. So it's clear that by Salem's construction, there is the exponential construction of proximity Salem numbers. And of course, the equality or not of T prime with S is a major unsolved problem related to many areas besides number theory and harmonic analysis, not only number theory. So, but one can actually do better, and I would say that the following principle is still a completely explicit and easy to prove inequality for discriminants of polynomials, not even with integer coefficients. It's still the same principle as Liouville, because it's based on dropping the following discriminant term, but positivity when the polynomial Q has integer coefficients. So this bound is about separable polynomials Q with complex coefficient of degree D, and for any set of 2k pairwise distinct complex roots of Q, which I want to pair up, but this is maybe just pairing up two roots, and even if, or pairing them all, and even when the sum is empty, this is still reduces to Malek's discriminant inequality, and the proof is a Van der Monde matrix after column operations and Hadamard's inequality. So hence this sequence, and Mignot has this general form for several roots. And of course the issue with this, why it doesn't give great results on separation in problems relating to the Lamer problem and similar things, is the discriminants are rarely much smaller than like the discriminants of cyclotonic polynomials, but we cannot prove that, right? This famous problem of Serre about exponential discriminants of polynomials. And so this case of Malek's inequality immediately gives you an exponential in minus n log n bound. This and various similar problems, some of them were actually for different numbers, were related to the dimensions of the Bernoulli convolutions and things like that, that are not my subject today. But I just want to say that often in situations like this, one has this sometimes hard, difficult problem about improving the strength of the general Mahler bound. As it turns out, this bound is not sharp, so I'll give you the sharp bound by a completely different method. So this is what I called the square root method. We have the...
Professor?
Yes.
Oh, sorry to interrupt. So the previous thing was for arbitrary, it's not just for like Salem. Are alpha and beta here?
Completely arbitrary algebraic numbers. It's actually even for complex numbers, it's just that then if you take Q is maybe the product of their minimal polynomials, so that they are distinct minimal polynomials, the coprime. And so this discriminant term is a non-negative. It's the logarithm of an integer. So you get a separation bound by dropping it. The problem is we're losing too much. We have a large discriminant secretly. So the square root method can give you, okay, you can take L equal to 2 if you want, but so I set a fixed interval, can give you an exponential separation bound for two numbers, both of which are either Salem or Pizot. Maybe the Salem case is more interesting, but the proof works uniformly. And so there are two ideas in this proof, which is kind of based on a functional method, not on discriminants like dropping discriminants by integrality, a completely different principle. So the first idea, the first idea by itself is obvious, that for every holomorphic function on a Riemann surface, perhaps I have just a domain in the complex plane or the Riemann sphere, and for any compact K, which in the applications is completely can be the union of Jordan arcs, like straight or circular segments, which pair up the zeros of the function inside the domain. So counting for multiplicities, so we suppose that each Jordan arc contains exactly 2 zeros of f. Then of course there is a single valued holomorphic square root function on the whole, on the complement of G minus K. So the idea is that we have a large analytic square root if the pairing is close, if the function is close to a double, to having double zeros. And the other ingredient, which is the arithmetic dimension, is the arithmetic rationality criterion of Hoya, that is somehow it adds an arithmetic dimension to an obvious to a basic analytic fact, which is the extension of Riemann's removable singularity theorem. And we can summarize that by saying that the capacity zero sets, will be a definition coming up, are exactly those that are invisible to bounded holomorphic functions. So bounded is a keyword in the possible or in the applications to Dirichlet, to L functions broadly, but bounded analytic functions extend automatically. Of course, it's not the problem just with meromorphic poles. It's completely false for unbounded holomorphic functions. It could be an essential singularity, but here is the arithmetic dimension. So you have the capacitance equal to 0, and the definition will follow soon, is equivalent to essentially equivalent, but implies the following intersection is a rationality criterion. So this is saying that the fraction fields of these two rings intersect in the rational functions. So this is the meromorphic functions on the complement of K in the Riemann sphere, which I consider expanded at infinity, 1 over x being the coordinate of the Riemann sphere, and kind of gluing a formal scheme to the Riemann surface via this identification of the coordinate. And I'm assuming that the power series formal expansion of the function at infinity has integer coefficients. If K is small in the relevant sense, which is the notion of capacitance, then every such formal function in this intersection is a rational function. The prototype of this theorem was yes.
Sorry, on the last slide.
Okay, come back.
Do you not need to hit all of the zeros of f with K?
Yes, all of the zeros. So suppose we have an even number of zeros counting multiplicities, and you choose some pairing, the kind of the smallest way, or any way that you
Or like, is there also a condition that K contains every zero of f?
K contains every zero of f, yes, that's what I mean. So exactly, yes, sorry, I wrote it not quite right, but that's what I...
Okay.
In this domain, yes. Because there is no monodromy around. If you have a control that doesn't cross any of the loops. So the genesis of these theorems was the remark of Emile Borel upon an essay of Hadamard, but it was first, so that was in between Borel and Work, there was Poya, but the first application to number theory was when Work in 1959 bypassed, I guess, so analytic cohomology was not sufficiently developed for this, and he was the first to prove the rationality of the zeta functions of varieties over finite fields. So by means of this proxy or this abstraction, so of the rationality criterion. So the case that so the theorem states that if we have a formal power series whose coefficients are integers, you might just expand at 0, and which has a positive convergence radius of the Archimedean place, but at a p-adic place, it's entirely meromorphic. So Dwork found a p-adic analysis procedure to present the zeta function recalled here as a quotient of two entire p-adic convergent power series, then we have a rational function. So the arithmetic part of this proof is summarized in this, the global part of the argument in this realm. The functions, the zeta functions, so this can be about finite type schemes over Z. In this case, we have essentially power series because we have a power series in Q to the minus S, where Q is the residue field cardinality. So we're talking about very different kinds of Dirichlet series. And the power series case is still within the usual the corpus of work on arithmetic algebraization theorems. There's been essentially nothing about can we use Diophantine arithmetic algebraization ideas to say something new about L functions in number theory. So just a quick display to say what the Malag-Mignot general separation bound gives in the case of Weil numbers. So this is a bit mouthful, I guess I want to say. Just consider a Galois stable set of Weil numbers, so algebraic integers, which are on all of whose conjugates are on the circle of radius square root of Q. But really, I take the case of A over a Abelian variety over FQ, and we take the one-dimensional part of the cohomology of phase. So we take the denominators of the zeta function on that relevant circles, 1 over square root of Q, and we take the polynomial, the reciprocal of that. And so I'm going to assume that the dimension of A is even, just because the case I have in mind are varieties geometrically isogenoous to the product of two G-dimensional Abelian varieties, so that we can discuss a pairing up of the roots. And we have the following quantitative measure to how we pair up, to how closely the roots are, or the Frobenius roots are to being double. So we can take, there is a unique minimal pairing of the Weil roots on the circle of radius square root of Q that doesn't cross the real axis at an interior point. We take the sum of the arc length in this minimal pairing.
What is shadowing?
That is my buzzword where did I? This is what I describe this is what I call delta V, because I think of almost double zeros when I say the zeros shadow, come in pairs, maybe zeros of B shadowing the zeros of C are what I...
So what does minimal here mean? Is it like you choose a pairing that minimizes the distance in...
I just go counterclockwise, but never, so starting from the real square root Q, I go this way, never crossing the roots, of course, are symmetrical. We have 2G roots up and 2G roots down, so I have G arcs above and the reflection below. If you think about, of course, I account for multiplicities. There may be a triple root somewhere. I can have zero length degenerate segments, but there is a unique pairing. There is not really a choice. And anyways, I just want to measure how closely, in some sense, was the...
What are the eyes here? Are the roots of some polynomial I should think about, or ZJs? Sorry, ZJs.
No, this was the notation before that. Okay, that was the general zeta function, and I just had too many things on the slide. But it's an extremely simple, just talking about Weil polynomials and nothing more. In fact, it's too simple.
No Salems right now.
No Salems. It is going to be an analogous bound. So I showed you. I still haven't proved the Salem bound, but I'll prove two bounds: one for Salem numbers and one for Weil numbers, and both of them are best possible. Just remarking that the general, so again, I look at the Malag-Mignot, the Liouville ideas, they give you a certain bound which is not optimal, but give an idea of what kind of separation we have, just because these Weil the Frobenius roots are algebraic integers. And if you compare to zeros of L functions, there is nothing to take place of the little bound, for example. And so the first question, this question I can answer right away. With the square root method, there is an optimal shape of bound on this shadowing tightness, delta V, that I defined, running through all Abelian varieties. That's just a question about polynomials with reciprocality and having the roots lie on the circle. But the real question I wanted to ask is in some sense it's the reason. Okay, it's a stumbling block for actually the interesting application. If there is a the first half that I'll describe has a almost perfect analog for Dirichlet functions, but the second part is already stuck at this elementary problem about function field arithmetic. And so I want to ask when you have A running through Jacobians, or maybe if you have this B cross C idea for products of 2 G-dimensional Jacobians, so just speaking about separation of their roots for curves, how much the general bound, this shape of bound, shall improve. So just on kind of statistical principles, because you have very roughly q to the g square abelian varieties, g plus 1 plus 2, but polynomially q to the g curves. This is consistent with this kind of bound up to the exponent, which is not optimal. But there seems it doesn't seem to be, I don't know of construction for curves that makes this delta arbitrarily small. We have the analogies in Katz and Sarnak, which formulated far-reaching conjectures about statistical correlations for zeros in families of automorphic functions, where one compares to analogous laws for Weil numbers in a certain double limit, where q goes to infinity and then g goes to infinity. So I can apply the linear distribution theorems. But if instead I can keep the circle fixed and take g to infinity, then we can discuss limiting distributions and, for example, on the fixed of Frobenius roots on the fixed circle. And in this regime, the idea in Drinfeld and Vladut, so in this regime, the general Weil upper bound on the number of rational points improves by simple algebra, just because you have, so this is the zeta function of a curve and the Frobenius roots or the reciprocals, and this is the explicit formula for the number of rational points over the successive extensions of the finite field. So these numbers have to be non-negative, and just using that system of inequalities give you an upper bound of improved upper bound and more with the same with the same technique. Vesselin and Vladut establish in fact that the limit measures of these Weil numbers, I mean Galois orbits of Frobenius roots on the fixed circle as the genus of the curve increases are nice. So they, unlike for general abelian varieties, they have a continuous density function, for example, and even kind of a hypothetical structure. They classify positive Weil systems instead of curves, but at least hypothetically, we have a complete understanding of those limits. But for abelian varieties, the limit measures can be anything. So, for example, one can say that there's a Bourbaki seminar lecture by Serre on this about Robinson's theorem and so forth. So the compacts on the circle that support at least one limit measure for abelian varieties, for Frobenius roots of abelian varieties in this regime, are exactly the ones that have a capacity at least q to the quarter, and the limit measure can be a counter set or extremely bad behaved. So this q to the quarter is actually relevant to the proof I will show. And so this is just so this is a picture of the Gaussian unitary ensemble density when speaking of the origins of these spacing laws. But the density plot, so this is the density for successive spacings normalized of the Riemann zeta function, and confirmed with Odlyzko's experimental computation very early on, and from Mechta's book. But of course,
sorry to interrupt. Are the limits you talked about last time? So is it like you're fixing Q and then you're looking at the average, like the distribution of the average distribution of A numbers over all curves of genus G? Like what? Like in the previous?
Yeah.
Like, are these averages over like at each G is
No,
this like an average
it
over all
is,
Q?
depends on which problem. So
Like in these three.
on this slide, yes, but here on this display, we just take a sequence of curves and we take all the possible limit measures that you can have, and even that is extremely well behaved. They have a density function.
Oh, okay. So you're picking a C for every G, not like averaging over all the C at each
sequence. And of course, it's a regime that is comparable to like bounded root discriminants, like Gauch of H towers. They have analogous theory for number of fields. But here, so this is just the Riemann zeta function, and this plot is not proved. But the idea that led Montgomery to conjecture things about, to consider the problem and figure out this density and the zeros correlations of pair correlations for the zeta function was the observation. So you look at the true plot and it shows. Okay, so there exist small spacings. This is like a density plot for the small spacing less than half of the average spacing, which is rare. The zeros have a repellency property, but it's compared to like the Poisson process, but it's still a positive density. But if we have Ziegel zeros according to whatever definition Montgomery was studying, then there are no small spacings less than a half, and this was an idea to prove lower bounds, effective lower bounds on class numbers of complex quadratic field, or rule out Ziegel zeros in a certain sense of the term. And it has been often recounted how Montgomery met Freeman Dyson at tea time at IAS, and they figured out that they had they brought together the subjects of Riemann zeta function and random matrix theory, but in fact I want to point out that it was the following idea, the following subject that intrigued Montgomery prior to this visit and when he began studying these things. So class number one is a classical historical problem in mathematics with several different solutions. But we go back to the first idea on the problem, considered by Max Deuring in 1933. So by means of which, with Heilbronn, shortly after they proved at least finitely many quadratic complex imaginary fields have class number one. That's an ineffective theorem, giving, and soon it crystallized into this like at most 10th phantom discriminant, and so forth, before effective methods were introduced on this problem. But the idea was essentially the same, and with modification it applies to Ziegel zeros, or at least the lower bounds on effective lower bounds on class numbers. So the idea is that if we have class number one, let's say along a sequence of discriminants, and then this would be so this is in any case the zeta function of the quadratic field, but it would also be an Eisenstein series. It is the principal. So this is the partial zeta function over the principal quadratic form, and this Eisenstein series specializes at a point very high up in the fundamental domain of height square root of d over 2, has, by the Fourier expansion, approximate formula. I mean, so it has a main term given by the constant Fourier mode of Eisenstein series, which is this explicit term, plus a very rapidly decaying error term, which and just Deuring applied Rouché's theorem to this situation. And so in this way, he found that all the zeros up to height square root d, also in the critical strip for the actual Dirichlet zeta function, which is a product of this the Riemann zeta function for accounting for half of the zeros asymptotically, thinking like maybe this discriminants sequence, and this fictional like exceptional character L function, accounting for the other half of the zeros. And so that studying the zeros of the x z function and finding them to be essentially, okay, so this story one can hear from Montgomery's lecture at this conference, the history of this idea. All the zeros of the main term, except for the zeros close to 1 and 0, are on the critical line and simple and approximately in an arithmetic progression. It's just zeros of this. And so in this scenario, since the zeros of zeta would be some subspace of the zeros of the product, which have a structure, then one would have that zeta has no zeros less than half the average spacing. And with the exceptional zeros scenario, this kind of conclusion can still hold statistically in terms of density of zeros. And the idea has still not been completed to try to disprove this statement for the Riemann zeta function alone. Now it seems the exceptional character is out of the equation. So, what is the idea that I want to apply power series methods in the study of Dirichlet series, like this L function that was maybe Dirichlet L functions. The Dirichlet series of function field arithmetic are sparse, and that is the distinguishing trait that whenever now for power series there is always a singularity on the circle of convergence, and if in general there's this definition of sparse Dirichlet series, this is the meaning of sparseness, the circle of convergence is the half plane of convergence, and again there is a singularity on the boundary of the half plane of convergence. And for L functions, of course, this is completely false, and there are different mechanisms for that analytic continuation, other than having linear differential equations and continuation along all paths, which avoid the singularities and so on. So we have modularity, and this is the Mellin transform of, for example, the theta function in the case of the Riemann zeta function, modularity or automorphy, and we have a pair of Dirichlet series which are linked by a certain functional equation, but the functions are initially given as absolutely convergent Dirichlet series in half plane and continued by mechanisms of modularity. So, now I will present the square root method. As I mentioned, this prototypical theorem with the simple proof structure, which is mirrored in the methods, in the various holonomy bounds that we have been developing for different applications. So this is the Riemann removable singularity theorem. It simply says that this is the ring of bounded holomorphic functions near a puncture on any Riemann surface. And the fact that, so this is true for precisely the zero capacity sets E. And the other existence theorem is the Riemann existence theorem in the following sense. And so,
Professor?
Yes.
Sorry, I could you say again the two theorems in the previous two slides? I wasn't able to read them.
Sorry. So we have compact Riemann surfaces.
And what is the one before that?
And the one before that is
How is this an algebraization theorem?
combining, yes, only in the sense that you combine the two theorems of Riemann when you're in a global setting, and ultimately you have the field of rational functions on a projective algebraic curve or something like that. So let me just give the arithmetic version, and this is the first real theorem. So this includes Poyat's theorem at the beginning. So we have a compact subset of the plane, stable in the complex conjugation. So there is the way I alluded to of gluing a formal scheme over Z to a Riemann surface. where the gluing is made by thinking of x as the coordinate of the Riemann sphere, and these two intersections of holomorphic functions and integer power series, respectively the fraction fields, give you the notion of holomorphic and meromorphic functions on this object. So this construction is in much more generality is in the recent monographs of Bost and Schar, called formal analytic arithmetic varieties, here of 2 dimension 2. And the algebraization theorem is saying that the capacity with the following definition, the one you have seen in, so this is the transfinite diameter, where E in this case is a subset of the Riemann's, compact subset of the complex plane. So transfinite diameter because we have Fekete's successive f diameters, which are decreasing, and the limit converges to transfinite diameter. And it's also the Chebyshev constant of the compact E in terms of auxiliary polynomial, in terms of monic polynomials and their exponential growth rate for the smallest growth rate of supremum of P over all the monic polynomials. And so this is exactly the notion for which the following theorem is true. One can, in a certain sense, so the Fekete and Seguin theorems are embedded into this. So the dichotomy whether the capacity of transfinite diameter of is less than 1 or bigger than 1. And so basically the following has a converse, let me say, in the opposite case. It's not exactly what on the nose. But so the algebraization direction ultimately tells us the formal function is rational, or more precisely, the holomorphic functions on E on this formal analytic arithmetic surface is effectively computable finitely generated Z algebra. And I had included a discussion of the proof.
Professor, is this, or sorry, what? Sorry, what are you proving? Is it
this theorem?
Oh, sorry.
At least this case, the essential case that we have intersecting the holomorphic functions on V with the integer power series. And it is an argument of Robinson's. So how the notion of capacity comes in, it amounts to existence of a non-constant, a non-zero integer polynomial, which is small on E, supremum less than 1, just like in the blueprint of Riemann's removal singularity theorem. And so this is exactly, turns out to be the same as this condition, Fekete's Seguin construction. And once we have this polynomial H, we're just trying, so the theorem amounts to both parts of the theorem about for large enough m, h to the m times the formal function, but this one is expanded at infinity and this is expanded at 0, will be a polynomial. So this is a Lorentz power series at infinity. So we want to, the task is to prove that all of its negative coefficients are 0. Those coefficients are integers. So I hope just to display the relation. So of course we're going to use that an integer is 0 as soon as it's less than 1 in absolute value. For large enough m, the integrand, where gamma can be any contour for this Cauchy integral, and we can make it to go around E, and taking it small enough, we still have we can ensure integrand less than 1 in absolute value. So this is how the theorem follows. And examples. So for example, when we take a slit, so the first was an obvious theorem, we have a deeper and deeper slit from infinity towards 0, and we have this intersection is still a finitely generated ring, but there is a limit to where we can run the slit. So this still will give you more and more functions, but when you go to depth 1/4, that corresponds to having the unit interval having the capacitance 1/4, we get a continuum intersection, no conclusion. So here. So here is another famous application of these ideas. related theorem, which is saying, so this is again the ring of bounded holomorphic functions, and it's a fraction field, intersect with fraction field of integer powered series, but now on the open unit disk is still the field of rational functions. So this case is somehow on the borderline, and it's special for making use of Parseval. And the idea being, as usual, to prove a sequence of Hankel determinants approaches here. And note that I have written an obvious theorem in the case of if I didn't have fraction fields, because a bounded holomorphic function by Parseval would have finite L2 integral on the circle in the limit sense, and that's the sum of the squares of the coefficients, so many of those coefficients vanish. And essentially the idea, so this is all essentially Salem's theorem, and the idea amounts to observing that the phenomenon extends to the fraction field with very nice positions and estimates ultimately based on Parseval for these Hankel determinants. And as a simple consequence, Salem proved conjecture of Vijaya-Raghavan, the numbers are called Pizot and Vijaya-Raghavan sometimes, that the Pizot numbers are a closed set. It seems that Vijaya-Raghavan had been the only one who believed it at the time, that they are not dense in 1 to infinity. This is the definition of the Pizot numbers. The difference with Salem numbers is that all they conjugate are strictly within the open disk. So we have non-reciprocal polynomials, and this proof has been explained in several of Salem's books, in fact, the one harmonic analysis, Fourier series related to number theory, and many other places. But the idea, this fails for Salem numbers, so that the first step is always to take this step, the quotient of polynomial by its reciprocal, and that would be constant if we had a reciprocal polynomial. And so the proof in a nutshell, suppose you have a sequence converging to lambda, we need to prove that lambda is algebraic and ultimately also a Pizot number. You consider those integer power series, they are regular in the circle, except for one simple meromorphic pole at the reciprocal of the Pizot numbers. But we have a sequence of bounded characteristics, as we can see by subtracting off the residue, the principal part of the pole. And so we have a normal family of holomorphic functions, those functions on the disk. And extracting a limit along a subsequence, we can find using, as always, that lambda n goes to lambda. One sees that kappa also converge, and we find limit. But on the level of the integer power series, the limit only means that the sequence stabilizes. So each coefficient stabilizes over the integers. And so in the end, we have an integer power series in the limit, which is also expressed as a bounded Nevelina characteristic. So it's a quotient in this fraction field domain, a quotient of two bounded analytic functions on D. And so once we know these things are rational, it's easy to conclude that this rational function has the requisite form. So we have another Pizot polynomial in the limit. And so the original application of the square root method was based on a simple observation that I'll use this notation of homoetic arithmetic surface attached to a planar compact. But for any integer polynomial p with p of 0 equal to 1, there are two, so this notation included integrality of the power series coefficients. This is some congruence modulo 4, and the notation includes raising all the roots of the polynomial to the second and the fourth power. So there's some construction which gives you an integer power series coefficient, series with integer coefficients, but it's also a holomorphic function on the complement of any pairing of the roots, as discussed. And so that's already analytic separation information that for any such pairing, the capacitance has to be at least 1. So this easily leads to proof of this problem of Shinzo and Zasset-Haus about the optimal maximum absolute value of a Galois conjugate of algebraic integers, not roots of unity or 0. In other words, of this form. But it also gives a proof of this exponential separation of Salem numbers by the same token. So if we have two Salem numbers, lambda and lambda prime, which I've re-indexed for notation purposes, and then I have the minimum polynomial p and those polynomials with raising the roots to second and fourth power, similarly for the other Salem number. And then I take the product of the square root functions. This will have if the lambda and lambda prime are for fixed interval and very close to each other, then we can find a compact K of capacitance less than 1. It's pure easy analytic estimates, but for which we have a single valued holomorphic branch of the square root on the complement of that domain. But this is an indication about where the congruence mod 2 or mod p squared for any prime is coming from. So we have this collision of the integral coefficients with the smallness of E, and ultimately that gives, by the same argument, to the best separation bound. Here, finally, is the sharp bound on Weil numbers. So this is the case of abelian varieties of FQ. So by the Honda-Tate theorem, for every abelian variety of even dimension 2G, so the conductor is a perfect square in this sense, exactly one of the alternatives holds. So it's either delta is 0, so that means A is geometrically isogenous to the square of another abelian variety of FQ, or delta V is not too small, and one can show that this exponent in the regime that the fixed G grows, this exponent is best possible when we have a bound which is polynomial in 1 over the conductor. It doesn't seem to help to use the system of inequalities of eigenvalues coming in the case of algebraic curves, because they are completely compatible with the uniform measure. There seems to be no contradiction, and that is a stumbling block to applications to number theory. So here is the argument of the proof of this bound. Exactly the same idea. You take the square root of the following polynomial. So we have some pairing alpha and beta along the circle in the manner that I described of the Frobenius roots. And so alpha I is close to beta y. And observe that since, because of complex multiplication, I mean the field adjoining the alphas and the betas has CN, and so there is the complex conjugation that commutes with all the other complex embeddings, and so these traces to Q to the interval minus 2 square root to 2 square root of 2 are still still a Galois stable set of algebraic integers, and so we have a formal function with rational coefficients, but also it has integral coefficients by the factor of 2 I've included, and so this belongs to one of those intersections. Integer power series in 1 over x intersect with complement of this set E on the circle that paired up the zeros. And so that gives you a similar separation bound. It just turns out to be better to take the traces to Q first in this way to get the optimal bound. And so the arithmetic rationality theorem gives you that the capacity of transfinite diameter of is at least 1, because obviously this is not a rational function. It's some kind of separation bound. It just remains to relate it to the arc length. And there is a relation between this union of segments in capacity and the capacity of the original circular arcs, functoriality of Robinson. The two are related by a rational function which is not a polynomial, but still the formula holds in this case. That's Robinson found, and this gives that the bound from Pouillat's theorem translates into this bound on the original arcs. So the Q to the 1/4 that I've mentioned before comes from this argument. Sarah's paper explains it. Observe now we have explicitly this sign of L over 4 capacitance for a circular arc on the unit circle with arc length L. And so we know explicitly what is the capacity of the rotationally symmetric configuration of n circular arcs that cover a given arc length L. It is this, just by the functoriality of capacitance. And it is easy to conceive, but not so easy to prove. It's a theorem of Caliste that the rotationally symmetric case maximizes transfinite diameter, so it's always an upper bound on the true transfinite diameter. So that just comparing, it remains to compare the lower bound on the capacity of the circular arcs with the upper bound from Caliste's theorem. I've scaled the circle accordingly, and it unfolds to exactly this delta of a lower bound. The automorphic functions of L theory are entire neuromorphic functions with growth order 1. They have their zeros in the complex plane, and there is nothing like the Galois group. But the L functions, Dirichlet series coming from geometry, like L function of a motive, has integer Dirichlet series coefficients by design from an Euler product. So the idea is to exploit at least on some level the functional, the Dirichlet series coefficients. The question is, can we find a counterpart to the previous discussion for power series, now in the realm of Dirichlet series? There is no Galois group, but there are, of course, like the idea of irreducible blocks and like motifs like zeta vs, a function of simple Billiard variety, and so forth. And there is the idea of simplicity of zeros, just like a Galois orbit of algebraic integers has disjoint. And so at least the previous arguments, which incidentally gave the optimal separation bound, never used the Galois group. At least this is maybe something. But it's not at all clear how can we find the modularity of the intersection of the Dirichlet series analytic and integral coefficients properties, and whether there may even be any idea of capacitance that is a theory of capacitance suited for Dirichlet series. But we have in the realm of L functions that look like that ultimately will become L functions of holomorphic modular forms of GO2 type. There is a passage that we can use, and in fact we have used implicitly already to the world of power series and arithmetic algebraization theorems, because if you have so this type of L function, this is having a modular form of some weight and level, means the symmetry functional equation is a symmetry of this sk minus s under this evolution in the following sense. So it gives one modular functional equation, Wn is the Fricke involution. And so, so this is the case where in fact, it suffices to prove algebraicity of the form with integer coefficients over the ring of modular forms. I mean, this is very special to this type of modular forms. This was actually why it is actually sufficient to do this because of recent or no longer so recent theorem with Frank Pellegari and ZhengTong, called the unbounded denominators property by contrapositivity of non-congruence modular forms. So this concerns finite index subgroup of PSL2Z, which do not contain any of these congruent subgroups, gamma, then, like the majority of the finite index subgroups. And so this is about the passage to from a thin group to a finite index subgroup. The following black box, if you like, it can be used like that. So the theorem stated that the Fourier series or integer power series with which converges on the Q disk where Q equals e to the 2 pi I tau and is modular for finite index subgroup and extends to the cusps of the group as a meromorphic function, is in fact converse modular for specific n. One n because I put didn't mess it up, the Q series expansion where n is in fact the least common multiple of the cusp widths of the group. And if we have algebraic relation, the origin of this f as basically if you have an algebraic relation and use a Fuchsian uniformization, this is where the finite index subgroup will come. If we have an algebraic relation, then we have a function which is algebraic over some finite covering of y of 2, and then we apply the theorem to gamma and conclude that f was a true modular form, classical congruence modular form to begin with. And so we are, so one approach to modularity is simply to prove algebraicity over the ring of modular forms. So the basic tool for this is the following refinement of the original lemma that we call arithmetic holonomicity theorem in the paper. And this is a theorem of Bose and Shaw in the new monograph on formal analytic arithmetic surfaces. It extends Poyar's theorem to multivalent domains. So technically it says that, so for given holomorphic mapping phi, now the datum is this gadget formal analytic arithmetic surface that is, I haven't defined formally, but its meromorphic functions are the following intersection. And so we have, the datum is a holomorphic mapping phi. We can view that it can be highly multivalent, but we consider gluing the disk to a formal scheme, formal spectrum of Z1 over X. And so the theorem is that if the pseudo-concavity condition is in place, so the derivative, the conformal size of this mapping simultaneous analytic uniformization of X and a function F, so to speak, is sufficiently big. If we have this inequality, there is absolutely no conclusion in the opposite inequality. Then this field is just a finite extension of the rational functions, and the degree is bounded by the following quotient that we have termed the holonomic quotient. And this is geometrically meaningful because, for example, this recovers Poyar's theorem, at least for univalent domains, for when phi is a Riemann mapping for the form that I've written down, because in that case, by Jensen, this quotient just reduces to 1, and so that is a rationality theorem, the quality of these fields. And so this is a way to measure up algebraicity. So if you have, in particular, such an f, as I already said, that f are algebraic functions by considering the powers. And so this is the integral converse theorem that follows pretty directly. It follows from these ideas when we consider the bounded denominators property from a different lens of converse theorems. So the statement I will read out, and just not to go over time. Apologies. What time did I start? Was it 30 or a little? Okay, I will close the discussion up. So with this slide and the next question. So over a number field K, we fix just one of the complex embeddings. And with that embedding, we throw F as a complex power series. And we take the Mellin transform, the formal Mellin transform, we write down this Dirichlet series with reference to only this one complex embedding. And so suppose you have two integers n and k, a formal power series with S integral coefficients for some finite set of places of k containing the Archimedean places, but which is also, if it has denominators, they must be small in the sense, pretty mild, that F still converges viatically on the open unit disk at every place, V in S. And the distinctive features of this theorem, the integrality, is that there is no, firstly, there's this integral coefficients condition I just spelled out, and there are no twists, so there's no like veil character twists at all. So, but it's just a different way of viewing the unbounded denominators property extended to theme groups instead of finite index groups. And so, suppose we have this L function, this Dirichlet series, convergent absolutely in a right half plane, and admitting some companion, which ultimately will be some companion Dirichlet series, where this F tilde will be the Fricke companion of F, also convergent now in some sufficiently left half plane, such that the standard functional equation of the GL2 type holds holds on in this ring of entire holomorphic functions bounded in vertical strips. So that means there is an analytic continuation process which connects the convergent Dirichlet series on the two sides. And then the conclusion is that F is in fact classical modular form for that weight and that level. And as I say, F tilde is the Fricke companion. The argument is, of course, we connect by the inverse Mellin transform that has to involve holomorphy on the whole complex plane, so that we can read off the functional equation of the L function like, okay, I'll just write it here, like, let's see. Okay, this was the sketch, like modularity relation. And then we are dealing with the problem of showing that this f of q function is algebraically dependent over the ring of modular fonts. But in the spirit of the functional arithmetic theorems, here is at least one example, one application to this difficult world of ground simplicity of zeros and kind of conjectural picture which implies trivially like all statements of this kind. But little has been proved, and one corollary is that for abelian surfaces isogynous to the abelian surfaces over Q, isogynous to the squares of an abelian variety, so that there exists a square root in abelian varieties, modular isogenies. They are exactly those for which the conductor is a square, and the L function is also a square as an entire holomorphic function, just because we have the formal Dirichlet series operation. So the proof goes through this construction. So we start with a Dirichlet series, take the formal square root that seems to introduce some mild denominators of 2, but they are mild, almost integral in the sense of the theorem. So when this series is formally turned to a Q series, it converges on the p-adic unit disk, and then the method is applied to the formal Q series with those coefficients. So this is contained in the statement of the theorem. And I think, so there was a sketch of this. I will close, but let me just say the idea is that there is already a trivial kind of simultaneous uniformization map on the borderline of these algebraicity criteria, because we have this kind of equality integral structure, and we are ultimately writing down what we're trying to prove is a modular function as a power series in another modular function, and we try to prove that power series is algebraic. And there is an overconvergence which is encoded in the functional equation. It is, at least this connects the method to usual arithmetic algebraization of Dirichlet series. And so this is the last slide that I will show. The project now connecting to separation bound for zeros of L functions is the following question. Let me just include it here. In the spirit of the functional theorem, what are the sets E in C for which one can extend this theorem formally for functional equations on the complement of E, not on the whole complex plane? So which sets in the critical strip? Of course, capacity zero sets have that property, but they are good for nothing, and we want actually to have some pairing of zeros. So last slide was like just the actual kind of pairing for products of L functions of this form. So this is like a formal Dirichlet series, which looks like the L function of a GL2 type, except that it's not holomorphic on all of C. And the methods of Diophantine analysis are effective, so there was a hope to connect to problems, difficult problems for separation of zeros, like zero zeros in restricted settings of this kind. More concretely, to give a new proof of class effective upper bound on class number 1 discriminants by the methods of Deuring and Heilbronn revisited. So, thank you for your attention. Apologies if I did go